Welcome, curious minds, to another deep dive. Imagine an AI that powers a critical decision, say, in finance, or maybe even healthcare. What if it gets it wrong? Not just once, but, unpredictably. Our deep dive today is all about building the engineering and technical safeguards to ensure that doesn't happen. We're plunging into a topic that's not just technically fascinating, but really critical for our future. How do we make artificial intelligence consistently precise and, crucially, reliably trustworthy?
Indeed. Yeah, the pursuit of more accurate and reliable AI, it isn't merely a technical puzzle. It's fundamental, a fundamental necessity for AI to be widely adopted. This isn't just about building smart machines. It's really about building dependable ones that truly deliver value.
Okay, right. Well, let's unpack this quest for dependable AI then. Our mission for this deep dive is to explore the key techniques, the strategies that help AI systems not just perform well, but do it consistently, reliably, making sure they work predictably for you.
Exactly. And to achieve that, we're really looking at several critical objectives. First, it's about minimizing errors. Simple enough, right? But also ensuring predictions are broadly representative and applicable, for diverse scenarios. Then, maximizing the AI's capacity for generalization.
Generalization,
Yeah.
meaning it works on new stuff it hasn't seen.
Precisely. Performs well not just on the data it was trained on, but also on completely new, unseen information. And a huge piece of this is fostering user confidence, creating systems whose results are understandable, transparent, predictable, which in turn encourages people to actually use them. And finally, we aim to ensure the robustness of the system.
Robustness. Like it can handle weird inputs.
Yeah, so it can withstand variations, unexpected inputs, noise, maybe even malicious attacks in the data.
Okay, that sounds like a tall order. Seriously. So how do we actually get there? What are the concrete steps, the goals involved in building this sort of bedrock of reliable AI?
Well, to achieve those objectives, we need to implement really robust data pipelines for collection, cleaning, pre-processing, the whole works. We must continuously optimize the models themselves through iterative adjustments. It's never really done. It's also crucial to establish rigorous evaluation frameworks, using thorough metrics, proper validation methods, and developing explainability capabilities is key.
Explainability, so the AI can tell us why it made a decision.
That's the goal, allowing AI to justify its decisions. Integrating effective human supervision is also vital for intervention and correction, especially in critical areas. And of course, guaranteeing data security and privacy, that's just non-negotiable. It's a truly multifaceted process, really, spanning from that initial data prep right through to continuous monitoring after deployment.
Okay, with those objectives and the high-level steps laid out, let's zoom in. Let's get to the actual toolkit.
Yeah.
Where do we begin when we're hands-on building reliable AI? It all starts fundamentally with the data, right?
Absolutely, 100%. The quality of data is the most critical factor. An AI model is only as good as the data it's trained with, period. We need high-quality training data, relevant, clean, meaning no errors, inconsistencies, duplicates complete, and truly representative of the problem the AI is meant to solve. And here's a key insight. Data that looks perfect on paper can still cause huge failures if its representativeness isn't really challenged rigorously.
Okay.
The presence of noise or outliers, for example, can significantly skew how the model learns. And it's not just quality. Adequate data volume is also essential. More relevant, quality data allows the model to identify more complex patterns, make more precise predictions. Insufficient data can often lead to something called overfitting.
Overfitting, right.
Yeah.
That's when the model basically just memorizes the training data, like a student cramming for a test. So it does great on the stuff it crammed for, but then completely bombs the real-world exam.
Exactly. Perfect analogy. And that leads to poor generalization. It can't handle novelty. Another crucial aspect is data diversity. The training data must cover a really wide range of possible scenarios. That helps avoid skewed outcomes and truly improve the model's ability to generalize to new situations it hasn't encountered before. And for supervised learning, correct labeling and annotation are also paramount. Inconsistent or just plain wrong labels, they can drastically reduce accuracy.
You've really hammered home the crucial role of data. Makes sense. But, even with perfect ingredients, the chef's skill matters too. So once we have that solid data foundation, how do we actually design and optimize the AI model itself?
Right, the model. Its choice and configuration are fundamental. It starts with selecting the appropriate algorithm for the task at hand. Not all algorithms fit all problems or data types. Then there's the meticulous process of adjusting hyperparameters.
Hyperparameters. Those are like the initial settings before training starts?
Exactly. Pre-training configurations, almost like dialing in the initial settings for its learning process. Things like the learning rate, or maybe the number of layers in a neural network. Techniques like grid search, where you methodically try, every combination, or random search, which is a bit more like an educated guess, help fine-tune these.
Okay. And since we're talking about models learning,
Huh.
you mentioned overfitting earlier. How do we actively prevent that? Encourage real understanding, not just rote memorization.
Good question. We use regularization techniques, things like L1, L2, or dropout. You can think of these as methods to sort of penalize overly complex models. They encourage the model to find simpler, more general patterns instead of just memorizing noise in the training data. Another effective technique is early stopping.
Stopping early, how does that work?
Well, we monitor the model's performance on a separate validation dataset during training. And we basically just halt the training when performance on that validation set stops improving or even starts getting worse. This prevents overfitting and optimizes training time. It's quite efficient. And for really complex models like deep neural networks, methods like gradient descent optimization and batch normalization are crucial. They ensure stable, efficient training.
Helping it learn without getting stuck or going off the rails.
Precisely. They help it converge better, leading to better accuracy overall.
So we start with solid data, check. That we carefully design and optimize the model, check. What's next in this continuous journey? It sounds like we need to actually confirm if our carefully crafted model is working as intended.
That's exactly right. It's an iterative process. It absolutely requires continuous evaluation. We need to define and use clear evaluation metrics that are appropriate for the specific problem. For instance, accuracy sounds good, right? Percentage correct. But sometimes it's misleading.
Oh, so?
Well, think about medical diagnosis for a rare disease. An AI could be 99% accurate by just saying no all the time. So for critical tasks like that, we often prioritize metrics like precision and recall, or the F1 score, which combines them. Knowing how many actual positives we missed, that's recall, or how many of our positive predictions were actually wrong, that's precision, is far more important than just the overall correctness percentage.
I see. The cost of errors isn't equal.
Exactly. Then comes rigorous model validation. This means using techniques like cross-validation. You divide the data into multiple subsets, like folds, and repeatedly train and test, rotating which fold is the test set. This gives a much more robust estimate of performance than a single split. We also use holdout validation. That means keeping a completely separate test set that the model has never seen during training or tuning. That's for the final, unbiased evaluation. And crucially, we must validate against ground truth, systematically comparing the AI results with data verified by human experts.
Makes sense. And I'm guessing it doesn't just stop once the AI is deployed and running out there in the real world, does it?
Not at all. That's a critical point. Continuous post-deployment monitoring is absolutely essential. Once an AI system is in production, we have to constantly monitor it. We look for things like data drift.
Day drift. Like the incoming data changing over time.
Yes. Maybe the characteristics of the input data change, like a sudden shift in customer demographics or sensor readings changing due to weather. Or we might see concept drift. That's where the underlying relationship between the inputs and the desired output changes. The old rules just don't apply anymore. We also look for emerging unrepresentative outcomes or just a general degradation in performance. All of these signal the need for retraining or adjustments.
So the model stays effective and, well, fair over time.
Exactly. It ensures it remains widely applicable. We also need to perform robustness tests, see how the model behaves with noisy data, outliers, slight variations, just to ensure stability in messy real-world environments. I actually recall a case where a small, seemingly insignificant change in how data was collected led to some really bizarre AI predictions down the line. And it was only through that rigorous post-deployment monitoring that they caught it before it snowballed into a major issue for users.
Wow, that really highlights the need for ongoing vigilance. This all sounds incredibly comprehensive. Building reliable AI is clearly a marathon, not a sprint. But ultimately, for AI to be truly adopted, like you said earlier, technical accuracy isn't quite enough. We need trust, right? So what are the additional considerations for building that reliability and, importantly, user confidence?
Yeah, this raises a really important question. Beyond just the technical precision, fostering that trust is paramount. One key area is explainable AI, or XAI. Developing models that can actually explain their decisions in a way that humans can understand is vital. There are tools now, like Lime or Heshape, These are powerful explanation frameworks.
Lime and HEShape, what do they do?
Well, LIME stands for Local Interpretable Model Agnostic Explanations, and S-shape for Shapley Additive Explanations. The real breakthrough with these isn't just seeing what features the AI used for a prediction, it's about starting to peel back the layers of that black box so we can finally ask why. And crucially, we can potentially retrain an AI that made a seemingly inexplicable decision. It sort of shifts AI from being this oracle we just have to accept to more of a partner we can interrogate.
That sounds incredibly important for building trust.
It is. And another critical factor is ensuring data representativeness and actively preventing skewed or unrepresentative outcomes. We have to identify and address issues in the training data, or maybe even in the algorithm itself, to prevent unfair or discriminatory results. This might involve pre-processing the data or using specific algorithms designed to promote fairness.
Okay, so AI shouldn't just be a black box we can't see into. We need to know why it's doing what it's doing, and we need to ensure its outcomes are broadly applicable, not skewed unfairly.
Absolutely. And alongside that is the concept of human in the loop. This basically means implementing mechanisms where humans can supervise, correct, or validate AI decisions, especially in critical situations. This ensures AI acts as a supporting tool, not a completely autonomous system, particularly where human oversight is really necessary. Then there are the foundational elements, data security and privacy. Ensuring data is protected complies with regulations like GDPR, for example, and protecting the model itself against adversarial attacks. And finally, transparency is key. Just being open about the AI system's capabilities, its limitations, its purpose. Being open with both users and regulators builds credibility.
Wow, that was truly a deep dive into the essentials of reliable AI. It's so clear now that achieving precise and reliable AI isn't just about, throwing complex algorithms at a problem. It's a continuous, holistic effort. It covers every single phase of an AI system's life cycle. It's fascinating, actually, to think how much of what seems like AI magic is really rooted in meticulous, almost mundane-sounding data preparation and validation.
Indeed. It really prioritizes the quality of data, the robust design of the model, rigorous validation, and fundamentally thinking about the broader implications of its impact. By implementing these techniques, we're not just improving the technical performance of AI systems, we're building the necessary trust for their full and beneficial integration into society.
So what does this all mean for you listening? You now have, hopefully, a comprehensive understanding of what makes AI trustworthy. It allows you to ask better questions, understand the nuances behind the headlines. But as much as we've covered today, the field is always moving, isn't it?
That's right. Yeah, despite all these advancements, significant challenges definitely remain. Think about the scalability of data. How do we efficiently manage and process these ever-increasing volumes of diverse, complex information? It's a huge hurdle. Or improving the interpretation of those complex black box models, like deep neural networks. We're getting better, but there's still a way to go. We also face the ongoing challenge of mitigating dynamic shifts in data representativeness, those drifts we talked about, that can emerge as models interact with the messy real world. And of course, developing AI systems that are more resistant to malicious adversarial attacks. That's a constant cat and mouse game.
It really sounds like the journey to truly perfectly reliable AI is very much ongoing. So thinking about all those remaining challenges, what specific part of this puzzle, maybe making those black box models truly transparent or perhaps anticipating how real-world data might subtly shift into great performance? What do you think will be the most significant challenge to overcome in the coming years for AI to reach its full trustworthy potential?